Continuing with linear transformations, consider their basic properties as functions. If you think back to pre-calculus and calculus, kind of properties we were interested in, when does a function 1 to 1? When does a function onto? When does a function have an inverse function? With the linearity condition, the answers come much easier than without. For here, we're interested in the property of 1 to 1. Now, if we have a linear transformation T from Rn to Rm, I can represent our linear transformation as multiplication by a matrix. So we're going to have a standard matrix A that goes with our linear transformation T. The recipe for getting A, for the ith column of A, I'm just going to evaluate our linear transformation on the ith standard basis vector. So that's going to have zeros everywhere except for a 1 in the ith row. Then, if I apply T to the vector U, that'll be the same as applying the matrix A to our vector U. For the 1 to 1 property, let's recall the definition. So if I have any map T from one space to another, that'll be 1 to 1 if whenever T of x is equal to T of y, we must have that x is equal to y. So what this says in terms of the picture, we have our x, we have our y, we apply T, they're never going to wind up in the same place. So if we were to say that T of x is equal to T of y, the only way that could happen is if we were starting off with the same points. So we'd have to have x and y were the same. To see that a linear transformation T is 1 to 1, we need only check that the kernel of T is equal to 0. Recall, the kernel of T is going to be the set of all vectors in our domain space, such that if we apply T to one of those vectors, the 0 vector comes out. Statement of our theorem, linear transformation T is 1 to 1, if and only if the kernel of T is equal to 0. In practice, we would check that by saying that the null space of A is 0. Now, in one direction, we'll assume that T is 1 to 1. We want to show that the kernel of T is 0. Because T is linear, T of 0 will always be equal to 0. Let's go be taking the spot of y in our definition of 1 to 1. If I have x in the kernel of T, so by definition, T of x is 0, then we have that T of x is equal to T of 0. Okay, they're both equal to 0. So x has to be equal to 0 by 1 to 1. That means if I try to find a non-zero x in the kernel, it can't happen. That means we have the kernel of T is equal to 0. In the other direction, okay, we'll assume the kernel of T is 0. I want to show that T is 1 to 1. Now, if I assume that T of x is equal to T of y, we can use linearity. Okay, I'll move one of these to the other side. Okay, and then I'm going to combine using linearity. So that'll say that T of x minus y is equal to 0. Now that means x minus y is in the kernel of T. And since the kernel of T is 0, that means x minus y is 0 or x is equal to y. And that gives us 1 to 1. Now, in practice, we're going to go to the matrix A and check its null space. Okay, recall the null space of A. It's going to be the set of vectors in our domain space, such that if I apply A to our vector, we get 0. Now, we've already seen the null space of A is equal to 0, if and only if the columns of A are linearly independent. And we can check that by saying that the row echelon form for A has a pivot in each column. Now, if we're trying to visualize 1 to 1, the idea is going to be lines will get carried over to lines, planes will go to planes, and so on. So if I have a linear transformation T, it's 1 to 1, it can distort these objects, but these objects are not going to get smaller. So let's take a look at some concrete examples. So we're going to have this linear transformation T from R2 to R2. I get the standard matrix A. Then I do some row operations to put it in row echelon form. So here I'm going to have a pivot in each column. So our T is 1 to 1. If we check what's happening on this grid in R2, we see that we're getting distortion, but the plane is getting carried to another plane. No points are going to map to each other. So 1 to 1. Other scenarios, low dimensions. We can have linear transformation T going from the real numbers to R2. So we'll just send X to the column vector XX. We have standard matrix A given by 1, 1. Put it in row echelon form, we have 1, 0. We have pivot in each column, so that's 1 to 1. Here, we see we're just carrying the real line to the line through the origin, y equals x. Now note, we're not hitting everything in R2. That's not a problem. 1 to 1 just promises we're not going to map 2 points over here to 1 point over there. Finally, if I have something going from R2 to R3, okay, we'll use this map here. We have our A matrix. We go to row echelon form. We have a pivot in each column. So we have 1 to 1. Then you'll note what's happening with our grid in R2. That's just going to get carried over to a plane through the origin in R3. So plane's getting carried to another plane. Distorted, but no 2 points go to a single point. For an example that's not 1 to 1, let's try the linear transformation from R2 to R2, given as follows. The A matrix is 2, 1, 4, 2. We go to row echelon form. I have a pivot only in the first column, so this is not 1 to 1. If I look at where our grid goes, it's going to carry the plane to the following line. So we see here, we're losing something when we map over. Now, if we go back to the definition of 1, 1, okay, we see that T of 1, 0 and T of 0, 2 both go to 2, 4. So I have 2 points that are not the same point, mapping over to the same point. So not 1 to 1. We have an immediate test for not 1 to 1. If we have our linear transformation gone from Rn to Rm with n greater than m, we're done immediately. So here we're going to have n columns, which is going to mean we have more columns in the rows, which means we'll never have enough pivots in row echelon form. So for instance, if I take the following linear transformation from R3 to R2, I don't need to do any work here. We're automatically not 1 to 1. If I do the work, I find the A matrix, then go to row echelon form, we see that we won't ever have a pivot in each column. Again, I could check not 1 to 1, but just trying to find 2 points that map over to the same vector in our range space. Later, we'll see quick tests for 1 to 1 when we have a square matrix. In that case, our linear transformation will be 1 to 1 if and only if our A matrix has non-zero determinant.